Well, good morning there, chemistry students. Hey, it's April 30th, 2020. Time to do some chemistry. Alright, so today we're going to do a little review of the bond energy that I had you work on yesterday. And then we're going to talk about some properties of covalent compounds. So, for you, I can name and describe some common properties of covalent compounds, and I can use the properties to distinguish between ionic and covalent compounds. So this was the exercise that I had put up on the board at the end of the video yesterday, and I had asked you to work on. So I gave you this equation. Methane is CH4, combines with oxygen, 2 molecules of oxygen, to form a molecule of carbon dioxide and 2 molecules of water. And so I wanted you to write Lewis structures out for each of those compounds and then figure out how many bonds you had. So you add up all the energy of the reactant bonds and then add up all the energy of the product bonds and determine if this reaction is exothermic or endothermic and how much energy is absorbed or given off. So, how do we do it? If you haven't already, please get out the exercise that you would have done. So here we go. What I did is I wrote out some formulas. So methane, CH4, it's got a carbon bonded to 4 hydrogen, single bonds. The oxygens, we're going to represent it with a double bond. That's not technically correct, but this is our simplified model. And there's 2 of them. Now, I asked you to write out Lewis structures. So on a Lewis structure, you show all the valence electrons. So we'd have more pairs of electrons on here. Okay, so each of the oxygens we would have drawn with 2 unshared pairs and 2 shared pairs. And then on the carbon dioxide, each oxygen has 2 unshared pairs. And on the water molecules, the oxygen has 2 unshared pairs. Okay, so those would be the Lewis structures. We don't necessarily need to see all those unshared pairs to be able to figure out the bonds, but you know, we're trying to practice your Lewis structures along the way too. All right, so now I got to add up the energy. Here's my arrow that separates the reactants from the products, and in my reactants, I have bonds between carbon and hydrogen, and there's 4 carbon-hydrogen single bonds, and there's 2 oxygen-oxygen double bonds. So if I add those up, well, 4 of those at 413 kilojoules per mole, and 2 of the 498 kilojoules per mole. Add that all up, we've got 2,648 kilojoules of energy that would be required to tear all these atoms apart from each other. Okay, remember, a bond is an attraction. To break an attraction, you gotta put energy in. On this side, I have 2 of these oxygen-carbon double bonds. And I've got 1, 2, 3, 4 of the hydrogen-oxygen single bonds. We add those up, and that says when we allow those bonds to all form, we get 3,466 kilojoules released. Oh, hey look, we get a lot more energy out than what we had to put in. So there's going to be a net outflow of energy in this case. So it's an exothermic reaction, and the energy released as written is 818 kilojoules. Okay, so as written, really we've got 4 moles worth of carbon hydrogen single bonds and 2 moles worth of these oxygen double bonds, etc. Okay, but as written, 818 kilojoules of energy released. Oh, you know what? We use methane as a fuel, right? That's the fuel for our burners in our lab. If you live in town, That's probably what you're using to heat your house, might be what you're using to heat your hot water, might be what you're using to heat your clothes dryer, okay? And what do? We combine it with oxygen, we burn it. We burn it for energy. We're looking for that release in energy. So we'd expect anything that we're burning as a fuel to be an exothermic reaction. Maybe just to mention, an endothermic reaction that you may have seen. Maybe if you're involved in athletics and you've seen those cold packs that you might have in the med kit. Now, oftentimes we just go get a bag of ice, right? But if there's no ice around, we usually try to have a couple of those cold packs, and you take them and you hit them or break them or bend them. And what's inside there, there's a chemical that's sealed in a container inside the bag, and there's another chemical inside the bag. When you break that inner container, the two chemicals mix, and they go through a chemical reaction, which turns out to be an endothermic reaction. And it absorbs energy from the surroundings. All right, now let's look at properties of covalent compounds. So first of all, when we use the word covalent, you can replace that with the word molecular. A molecule is a neutral group. I'm going to highlight that neutral right there. A neutral group of covalently bonded atoms. So the thing that's special about a molecule is it acts like a distinct group, and it's independent from everything else around it. So we saw in the burning methane, we produce carbon dioxide, CO2. And that molecule can exist as one single molecule. It's got 2 oxygen and 1 carbon. That group of 3, now wherever one goes, the other goes. They're attached to each other as an independent particle. Now contrast that with ionic bonding or metallic bonding, and you don't have any distinct units. You know, effectively in a metal, all the atoms are bonded. You know, if I got an atom right here, it's attracted to all the atoms around it, and those atoms are attracted to all the atoms around them. In an ionic crystal, all the negatives are attracted to all the positives, and all the positives are attracted to all the negatives. There's no distinct unit, but in covalent compounds, there is. They are molecular. Covalent compounds tend to have rather low melting points. So here's my jumble of molecules. And while these atoms are strongly attached to each other, there's nothing really that's holding, or very little that's holding this molecule to these other molecules. So the individual molecules can separate from each other. They don't get held tightly together. And if you think about it from the flip side, what makes something a solid is the fact that everything's being held really tightly together. Well, these aren't. So a lot of molecular compounds, they might be solid at room temperature, but they're quite easy to melt. Just a little bit of extra energy will melt them. Compare that to ionic compounds or metallic bonds. You have all those positives attracted to all the negatives, and it's very tough to tear those apart. And so they tend to have relatively high melting points. If we take it one step further, we've got a property called volatility. Okay? To be volatile, or a property of volatility, refers to how easily a substance can become a gas. And so, because these molecules have little attraction for each other, not only can they melt easy, but they can go into the gas state very easy. Now, I did want to remind you here, the bonds are still not being broken. That oxygen is very strongly bonded to that carbon, and also on this side. But that molecule is not strongly attracted to these other ones, so it can turn into a gas. Ionic compounds are solids, high melting points. They don't want to become a gas at all. metals, most metals have relatively high melting points. There's a few that are a little bit lower and become liquids, but I don't know of any metals that become gases easily. There's too much attraction for each other and they hold together. But covalent compounds can become gases. Now, because they can become gases easily, because covalent compounds are volatile, well, some of those molecules might go into the air. And they mix in the air, and of course they get to our nose and we breathe in, and